Welcome back to AI on AI, where we go deep on what's actually moving the needle in large models, architectures, systems, and strategy. Today's theme is Speed Always Wins, and we're unpacking efficient LLM designs from linear sequence modeling and sparse attention to MoE, hybrid stacks, and the very new wave of diffusion LLMs.
Thanks for having me. Let me set a business lens quickly. Leaders want capability, but they need cost predictability, faster latency, and lower energy draw. The reality is that long context RAG, agentic loops, and multi-step reasoning are creating bursty, expensive sequences. So the winners will be those who turn quadratic costs into linear or at least constant time per token at decode without breaking quality.
And the bottleneck is often not flops, but I/O. On GPUs, attention is memory traffic bound, not compute bound, which is why flash attention was such a watershed. By making attention I/O aware and fusing softmax, we cut global memory reads-writes and keep tensor cores hot. Flash Attention 2 improved work partitioning, and FA3 unlocked Hopper TMA and WGMMA so memory prefetch and matmul's overlap. That's speed you can feel in wall clock.
On the modeling side, linear sequence methods have converged. Linear attention, linear RNNs, and state space models all compress context into fixed-size states that update recurrently. Mathematically, many can be written as ST equals AFT T-1 plus BT VT KT, then read out with OT equals ST QT. The trick is adding data-dependent gates, stable feature maps, and more recently, delta rules that remove stale associations.
And don't sleep on conditional compute. Sparse mixture of experts switches on a tiny subset of parameters per token. Modern routing moves beyond vanilla top K softmax into expert choice, balanced assignment, hash routing, and adaptive K. Done right, you get the parameter count of a giant with the inference cost of a mid-size model.
I'll fly a parallel path. Diffusion LLMs flip decoding from left to right to denoise a full canvas. They deliver parallel token updates per step, better controllability, and bidirectional context. Yes, we're bridging to AR with blockwise autoregressive diffusion and continued pre-training of AR checkpoints into diffusion, so you can keep KV cache benefits while gaining faster sampling.
Let's go deeper on linear sequence modeling. The audience keeps asking, how do these models approximate softmax and still recall long-range facts?
Start with feature-mapped attention. Instead of X per QK, we use 5Q5K and aggregate keys and values into a running state. The state updates in 001 per token, so no n by n matrices. Early versions had smooth attention that missed sharp spikes, but later mappings and normalization, focused kernels, normalized exponentials, improved spiky, low-entropy behaviors critical for recall.
Hardware note, linear recurrences alone don't guarantee throughput. GPUs love big matmuls, so chunked parallel kernels are essential. Lightning-style and flash linear attention kernels run intra-chunk matmuls with inter-chunk recurrences, so you get matmul efficiency and linear scaling. Also, Blalock scan variants let you parallelize recurrences in training.
Right, and gating saved accuracy. Gated linear attention and related methods add data-dependent forget and input gates, so state doesn't just accumulate noise. Then the delta rule, Widrow-Hoff, turns updates into ST equals ST-1K KT-VT, KT's the T, actively unlearning wrong associations. Models like DeltaNet, Gated DeltaNet, and MesaNet push this further, approaching supervised online learning inside the sequence model itself.
There's a quiet unification happening. If you write the update as the argmin of a local L2 objective, minimize minus SK squared plus L2 regularization, you recover many fast weight recurrences. Go multi-step, and you approximate a sequence of householder-like reflections. Go global, recursively squares, and you get Mesa-style updates with analytical recursions and high stability.
For leaders, the translation is, linear sequence models used to be a calculated bet on efficiency. Now they're a configurable knob. Forget gates for stability, delta rules for plasticity, and scan kernels for throughput. You can pick variants to match business SLAs without wholesale retraining.
Give us a concrete story. Where did linear pay off without tanking metrics?
A document analytics platform went hybrid, linearized most layers with sliding local softmax windows and left a minority as full attention. Throughput rose about 2.5 times on 128K tokens, while long document QA recall increased roughly 8 points due to well-placed full attention anchor layers. Result: fewer SLA breaches on monthly peaks by near 18%, and incident tickets on slow answer dropped materially.
That worked because they used grouped attention on the full ATN layers. GQA over MHA reduced KV cache by a large factor, while flash attention 2 handled the rest. Don't underestimate grouped attention as the single most pragmatic inference win.
And they used LoRa to adapt after linearization. A few basis updates restored in-context learning. That's the Liga low LCATS point. Reuse pre-trained weights, plug in gates and low-rank adapters, and converge with tiny fine-tunes.
Speaking of grouped attention, can we unpack MQA, GQA, and MLA, and then the newer GTA, GLA? MQA shares one key value per all query heads. KV cache plummets, latency drops, but you sometimes lose quality. GQA groups queries and shares a KV per group, speed near MQA, quality near MHA. MLA goes further, compress KV to a latent tight cache, but you need careful handling of position encodings. GTA ties K and V into a shared projection reused across small groups, cleverly factoring rope so cache shrinks about 2 times while quality holds. GLA shards the latent KV, so tensor parallel plays nice, no full replication, and speculative kernels see up to 2 times speedups over previous latent schemes.
Strategically, I advise start with GQA for minimal risk, measure perplexity and task deltas. If your distribution has many short turns but heavy fan-out, GTA gives you cache savings at almost no loss. High-end inference farms serving mixed batch sizes gain from GLA because sharded latent KV scales gracefully.
Let's widen to sparse sequence modeling. Static versus dynamic via training-free sparsity. What's the state of play?
Static sparsity, longformer, big bird, mixed sliding windows with global tokens, predictable and fast. Dynamic sparsity, LSH routing ABC, adapts to content. Newer native sparse attention optimizes for hardware with hierarchical selection and blockwise Varlan kernels, and MOSA treats heads as sparse experts that pick top K tokens. Compute goes to the useful interactions.
For inference, training-free methods shine. Seer attention learns a gating mask by distillation and then prunes blocks at prefill. Streaming LLM keeps attention sync tokens plus a small window. Heavy hitter methods like H2O preserve the most influential tokens. Block paging like Quest or Longheads selects only relevant pages per head. Together, they tackle prefill, compute, and decode bandwidth simultaneously.
Kernel level, block sparse, flash attention skips dead blocks. NSA and MOBA unify irregular sparsity with segment length tensors, keeping SRAM access regular. We're seeing 9 times forward speedups at 64K tokens in some setups, and dramatic backward wins in training. I'm hearing 3 levers: linear recurrence, grouped attention, and sparsity. Where does MOE fit so it doesn't explode routing overhead?
MOE is conditional compute across parameters. The pitfalls: load imbalance, token drops at capacity, and instability. Token choice routing is easy but imbalanced. Expert choice balances perfectly but can leak future tokens in autoregressive settings, so people add estimators or constraints. Base optimizes assignment during training and uses greedy inference. Hash routing fixes routes via a table. Cheap and balanced, enough in practice.
Instability often comes from the gate. Softmax pushes competition. Switching to sigmoid or cosine similarity gates helps avoid representation collapse. Also, auxiliary balancing losses at micro-batch granularity can suppress specialization. So global batch balancing, aggregate loads across micro-batches, lets experts specialize by domain while staying balanced.
Adaptive K is hot. Top P-style routing activates as many experts as needed to pass a confidence threshold. Or you add null experts, zero compute experts, so routing remains top K, but some paths skip actual FFN. This saves cycles without re-architecting everything. Think of it like a just-in-time pit stop. Only cars that need it pull in.
Business case. A multilingual assistant moved from dense FFN to fine-grained MOE with global batch balancing and sigmoid gates. Training stabilized early, inference tokens per second rose roughly 1.7 times at fixed quality, and on specialized domains, legal and medical, win rates improved mid to high single digits since experts could truly specialize.
Just remember, routing itself can become the bottleneck. Keep gate projections cheap, shard gate parameters sensibly, and profile comms. MOE shines when you keep the router small and the experts large. Contrarian time. What is everyone missing while chasing these architectural wins? I'll poke the bear. Too many teams chase linearization first. In production, the real bottleneck is KV cache bandwidth in decode. Switching to GQA, GTA, and quantized attention, INT8 or FP8 with microscaling usually gives immediate double-digit latency reductions without retraining. Then prune KV with heavy hitter or page selection. Architecture swaps are powerful, but cache bandwidth pays the bills tomorrow morning.
Fair, though I'd argue linear helps pre-fill at very long contexts where softmax becomes untenable. The right heuristic is fix KV cache and I/O first, then linearize or hybridize for the last mile efficiency, or for ultra-long sequences.
I'll add, MOE conversion from dense checkpoints is an underestimated path. Sparse upcycling, copy FFNs and add a gate lets you scale capacity without new data from scratch. Combine that with grouped attention and block sparsity, and you've got a practical staged path.
And my contrarian note, diffusion decoding changes the shape of the entire debate. If you generate 20 tokens per step over 5 steps, the KV problem looks very different. Plus, fill in the middle and strict formatting are simpler. There's less sampling gymnastics.
Since we're here, deep dive on diffusion language models. What's the training signal, and how are they closing the gap to AR?
Start with a forward corruption that randomly masks tokens at ratio t between 0 and 1. The model learns to predict the masked originals conditioned on the corrupted sequence. The loss is basically cross-entropy over masked positions, scaled by 1t, which forms a variational upper bound on negative log likelihood. Unlike fixed mask MLM, random ratios make it generative. At inference, you start from a noisy canvas and denoise in a few steps. Parallel token updates.
Bridging to AR, block diffusion makes the sequence autoregressive in blocks. Keep KV cache across blocks, but denoise within each block in parallel. That yields flexible length outputs and reduced sampling steps. Alternatively, continue pre-training an AR model under diffusion-style corruption, differlamma, so you inherit in-context skills and then gain parallel decoding.
Reasoning? A recent recipe SFTs on chains of thought then applies a diffusion-friendly RL using a one-step log-prob estimator regularized by random masking. On math and logic benchmarks, the diffusion policy learns stable multi-step reasoning without the AR exposure bias. We're early, but it's a credible second track for thinking models.
Systems heads up. Diffusion can be compute-heavy per step, but fewer steps, good batching, and FA3 FP8 pipelines make it practical. The win is not just speed, it's also controllability. Length priors, structure priors, hugely valuable for enterprise forms and workflows. Let's ground with more case studies. What did teams actually do, and what happened?
A contact center platform swapped MHA for GQA, enabled Flash Attention 2, and added INT8 kernels for QKT. Latency dropped roughly 35% at steady-state traffic, first token time improved notably, and customer satisfaction ticked up. There was no fine-tune needed. Pure systems gains.
An LLM search company used SEER attention for prefill and H2O heavy hitter eviction for decode. Prefill speed tripled on 200K token inputs, KV memory fell by about 40%, and answer relevance metrics stayed within a single point. They later added GTA to cut cache further without observable quality loss.
A biotech literature miner linearized middle layers, left every fourth layer as full attention, and used LoRa for realignment. Throughput doubled on 256K contexts, and long horizon citation tracing accuracy actually increased since distributed full atten anchors improved global routing. Engineers reported training stability benefited from L2 regularized delta rule updates.
Hybrid architectures are clearly a sweet spot. Walk us through the interlayer and intralayer patterns.
Interlayer, alternate linear blocks with full attention. Mamba attention mixes, like Jamba or Zamba, use ratios like 7:1 or 4:1. Samba replaces global attention with sliding windows for extrapolation to million token inputs. These stacks keep compute mostly linear, while using full attention layers as refresh or synchronization points.
Intralayer, headwise mixing, some heads linear, some softmax, or sequence-wise mixing, local softmax window over recency, linear for the history. Himba does head split with meta tokens and KV sharing. LowLCats trains in 2 steps, attention transfer then small LoRa fine-tune, and recovers large models with minimal parameter updates.
Don't forget KV sharing across layers. Yoko generates a single KV cache and reuses it. It's a form of architectural cache deduplication, great for memory footprint. Combine with grouped attention, and server capacity jumps.
Strategically, hybrids are low risk. You can A/B which layers remain full attention via sensitivity tests. Often early and penultimate layers are spiky and worth keeping dense, while mid-layer highways can be linear.
We've danced around quantization. How far can you push attention precision before you dent accuracy? INT8QKT with FP16PV is an easy win. Sage Attention fused kernels make it plug and play. INT Flash Attention runs the whole attention in INT8 with tight error. Pushing to 4-bit is doable with microscaling per block. Sage Attention 3 uses FP4 for both matmuls with per-tile scaling. For training, sub 4-bit is emerging via distillation, but most production teams standardize on INT8 or FP8 for safety and throughput.
The trick is outlier smoothing, per-channel scaling, and respecting headwise scales. Keep softmax in a slightly higher precision, or normalize carefully. For long context, quantized KV cache on CPU plus shadow KV on GPU, like shadow KV, plays nicely with speculative decoding.
Let's address conversion and upcycling. How do you get MoE or linear without burning months?
For MoE, moification splits FFNs into experts using coactivation graphs. Sparse upcycling copies FFNs and introduces gates. For vertical sparsity, MoD treats layers as experts and routes tokens by difficulty. Branch train mix merges expert LMs into MoE layers and trains only the router. These convert dense checkpoints into sparse architectures with modest extra pre-training.
Linearization. T2R swaps attention for recurrent blocks, then fine-tunes. LowLCats does attention transfer with LoRa. Lyja reuses pre-trained projections to build gates and avoids extra parameters. Mamba in Llama distills layer by layer with hidden state alignment and speculative decode. The common pattern, reuse weights, keep residual shapes, fine-tune on a tiny token budget.
That enables weekend migrations. You pilot on non-critical services, see 152 tums throughput at ISO quality, then expand. Incidentally, this staged approach aligns with risk committees. Small change, big learning.
I want a methodical playbook. If you're a CIO staring at ballooning compute bills, what's first, second, third?
Step 1, diagnose where you're I/O bound. Profile decode bandwidth and KV cache. Step 2, apply grouped attention and FA23. Step 3, enable training-free sparse prefill if you serve long prompts. Step 4, introduce KV pruning with heavy hitter page selection and where safe INT8 FP8 attention. Step 5, pilot hybridization or linearization in mid-layers and recheck task deltas. Step 6, consider MoE conversion for capacity-limited domains. Throughout, set guardrails using a no more than 1 point drop rule on your top 5 business KPIs.
And test kernels early. Many gains are kernel level. Align sequence lengths and batch shapes to kernel sweet spots. Pin memory and exploit TMA WGMMA. Systems shape models, not the other way around.
On the modeling side, map your tasks to memory needs. If you need sharp retrieval, retain some dense attention. If you need long-run stability, favor gated recurrence and delta rule updates. Mix wisely.
For MoE, start with coarse sparsity, few experts, low K, and scale after measuring specialization. Minimize gate complexity to keep routers fast. Prefer global batch balancing to avoid specialization suppression.
If your workload loves strict output formats or fill in the middle, spin a diffusion pilot. Even 5-step denoising with blockwise AR can be faster than left to right for structured tasks. Tiebreak with latency measurements, not vibes.
Any cross-modal lessons we should steal from vision and audio? Vision folks have been factorizing attention along axes and time for years. In long video, dilated and axial patterns win. Not every position needs every position. Audio adopted bidirectional Mamba to capture non-causal context. Both domains show that structured sparsity, not just random pruning, preserves semantics.
In imaging, state space models fused with local attention beat pure approaches. Likewise for text, a log linear memory for the far past and a local dense window for recency is a robust pattern.
And from a product angle, omni models eat more context, so the efficiency dividend compounds. The same sparse and grouped tricks that shrink text KV shrink visual and audio caches, enabling new real-time interactions.
Quick fire. Favorite speed heuristic each of you lives by?
Strategy is resource allocation. If it doesn't change latency or throughput at peak, it's not a strategy.
Move bytes once, I/O dominates, so fuse kernels and keep data on chip.
Forget to remember. Good forgetting gates are how long context models avoid drowning in their own memory.
Specialize or die. If your experts don't specialize, you built an expensive, dense model.
Parallelism beats cleverness until it doesn't. Use it, but don't miss modeling advantages like diffusion's controllability.
Before we wrap, one more debate. Is the future linear, sparse, or diffusion? Near term, sparse and grouped attention plus quantized kernels, it's the cleanest operational win.
Midterm, hybrids where linear does the heavy lifting and full attention corrects. Delta rules make linear smarter over time.
Scale term, sparse MOE over hybrids, capacity without linear growth in compute is the only way to keep pushing capability envelopes.
And a parallel stream, diffusion for structured tasks and multimodal alignment, coexisting with AR, blockwise hybrids will blur the line anyway.
The business answer is and. Use the smallest set of tactics that delivers your SLA and margin, overfit to your workload, not the trend.
Final rapid advice. What gets you a measurable win this quarter? Turn on GQA, FA2 or FA3 and NT8Q key measure. If decode is still slow, apply GTA and KV pruning by heavy hitters.
Linearize a tranche of mid-layers with LoRa realignment. Retain every fourth dense attention layer. You'll likely double prefill throughput on long contexts.
Upcycle to a small MOE in the most domain-skewed service. Start with low K and global batch balancing. Watch specialization emerge.
Pilot block diffusion decoding for forms and infilling workflows. You may have steps with better format adherence.
Rapid in governance, performance budgets per model, and an efficiency backlog that product managers actually prioritize.
That's a masterclass. We covered feature-mapped linear attention with delta rules, FA3 kernels with WGMMA TMA, grouped and latent attention, dynamic sparse and training-free masks, MOE routing and balancing, hybrid layer design, and diffusion LLM bridges, plus real deployment playbooks. Thank you all for the rigor, the debate, and the field stories. Always fun to trade kernels and scars.
And to sneak in a delta rule or two.
I'll route myself to the nearest coffee now.
I'll denoise that plan in 3 steps.
And I'll gate our enthusiasm with measured rollouts.
Perfect ending. Speed wisely, folks. See you next time. Welcome to part 2, our implementation deep dive. We're going to turn the survey's blueprint into an actionable playbook across 3 lanes: kernels and I/O, memory and caching, and modeling choices. We'll punctuate with deployment stories and the few gotchas that bite. Let's start with I/O-aware attention, because that's the move bytes once layer. Flash attention 2 wins by row-wise tiling and a 2-pass causal diagonal, minimizing SRAM thrash. On Hopper-class GPUs, flash attention 3 adds TMA, async global to shared loads, and WGMA, warp group tensor core MMA, so you prefetch KV while doing QKT on tensor cores. Producer warps feed, consumer warps multiply, softmax is interleaved. If you're tuning, choose tile sizes so shared memory banks aren't contended, e.g. make head dim a multiple of 64, keep occupancy above 50%, and bias toward FP8 with per tile scales for matmuls while keeping softmax accumulations at FP16, FP32 for stability.
On the modeling side, linear sequence modeling lives or dies by 2 things. 1, stable feature maps, and 2, intelligent forgetting. For feature maps, normalized exponential or focused kernels mimic softmax's spiky weights. For forgetting, gated linear attention, Alpha T and beta T, learned from the current token, removes stale associations. Adding delta rule updates brings supervised unlearning. ST equals ST minus 1 minus ST1 KT minus VT KTT to keep training stable. Regularize with ST2 and apply layer norm to S or its readout. For throughput, use chunked parallel kernels. Intra-chunk mapmol with inter-chunk recurrence. This is where Blelock scans shine during prefill and training.
For MoE, the practice is simple router, balanced loads, stable experts. Token choice routing is easy but imbalanced. Balance via either A, global batch load balancing, aggregate loads across microbatches before computing loss, or B, bias-based, auxiliary loss-free reweighting of gate scores. Keep the router small, single linear plus temperature, to avoid comms overhead. If instability appears, experts fight, swap softmax for sigmoid or cosine routing to damp competition, lower temperature, and add a shared expert residual path that's always on. Capacity factors near 1.0 with a dropless strategy plus null experts, zero compute, let you do adaptive K without dynamic control flow.
Grouped and latent attention is the other low-risk lever. Migration plan, MHA, GQA, group size, GTA, tie K and V, with careful rope handling, broadcast the rope-dependent component per group, GLA, shard latent KV per tensor parallel slice. Checkpoints uptrain quickly because only KV projectors change. The KV cache shrinks roughly proportional to groups, and speculative decoding benefits when your latent is sharded rather than duplicated. Watch your kernels. A custom grouped attention kernel beats naively repeating heads.
For diffusion LLMs, implementation is about the corruption schedule and the sampler. Training uses random mask ratios 0-1 with a 1T weighting, so the model learns everything from light edits to heavy denoise. Inference runs 4 to 8 denoise steps with parallel token updates per step. To bridge to AR, run blockwise AR, keep KV cache across blocks but denoise within a block, so you're flexible length but still parallel. For reasoning, do SFT on chain of thought traces, then RL with a one-step logprob estimator regularized by random masking. Practically, you'll want a bidirectional attention backbone and a structure prior during decoding, e.g. expected length distribution or schema tokens, to lock down formats.
Let me compress that for business leaders. Step 1. Turn on grouped attention in modern Flash kernels. Step 2. Shrink KV traffic with latent grouped variants and training-free sparsity for prefill. Step 3. Hybridize or linearize only where sensitivity is low. Step 4. Scale capacity via MoE with load balancing gates. Step 5. Pilot diffusion decoding for structured outputs where parallelism trumps left to right. In each step, track a small KPI pack. P95 latency, throughput per GPU, long context recall, and top 5 task win rate.
Great. Let's dig into prefill versus decode specifically. People keep mixing them up in dashboards. Prefill is compute-bound. Decode is bandwidth-bound. So, prefill deploy. Sear-style learned block masks or MoE heterogeneous window sizes and block sparse flash attention to prune attention tiles. Use compute-friendly chunk sizes, e.g. 128 to 256 tokens per tile, to sustain tensor core utilization. Decode. Attack KV. Switch to GQA GTA. Prune KV pages with heavy hitter or query-aware retrieval, quest-like paging, and offload to CPU with compressed product quantized cache, PQ cache, while a shadow GPU cache feeds speculative decoding. If you see memory stalls, you're bandwidth bound. No fancy model will save you until that cache footprint drops.
For long context recall, a hybrid memory stack often wins. A small sliding window softmax for recency, linear gated memory for the middle history, and a sparse cache of critical key value pairs, selected by gradient or attention magnitude for exact recall. If the model drifts, plug in a delta rule learner so it can overwrite wrong associations quickly. Think of it as an online RLS that supervises the fast weights.
MoE-specific serving tips, pre-compute gate projections per sequence chunk to avoid recomputing per token. Pad expert microbatches to uniform shapes for efficient all-to-all. Pin memory buffers per expert to minimize allocator churn. If internode traffic is your ceiling, co-locate experts by affinity, domain labels, and keep hot experts replicated. For training, gradient accumulation across microbatches plus global batch balancing yields both throughput and specialization.
A retailer's assistant stack applied this. grouped attention plus block sparse prefill and page-level KV pruning. They saw roughly 2 to 3 times prefill speedups on 200K token sessions and about 30% lower P95 decode latency. The kicker was fewer, still thinking timeouts in peak hours. Customer happiness metrics followed.
Let's detail linearization workflows. People want the weekend migration.
The lightest path is attention transfer. Freeze most weights, replace attention with linear recurrent, gated S, feature map phi. Distill on teacher attention outputs for alignment, then a tiny LoRa fine-tune recovers downstream tasks. Keep a dense anchor every 3 to 5 layers. Set alpha gates to a moderate lower bound to avoid state washout. For instability, normalize 5Q and 5K, and cap door SR via weight decay on S. If you want no extra parameters, reuse K projections as gates, Liga style, and keep the residual shapes unchanged. On long contexts, set intra-chunk 256 and inter-chunk scans. It's surprisingly plug and play.
One caution: linear recurrence can be slower than softmax on short sequences if you don't chunk. Always run chunk Triton kernels and fuse gate computations. Also, choose phi with low variance so matmuls don't explode. With normalized exponentials, per head scale constants help.
And don't boil the ocean. Pilot on document Q&A or summarization services with known latency pain. It's easier to show a 2 times throughput win there than on short chat workloads.
Okay, quantization specifics for attention and KV. How low can you go? Safe baseline, IN8 for QKT and FP16 for PV. That's the Sage-style 8-bit first matmul pattern. Usually invisible quality impact. Next step, in-flash attention. IN8 throughout with FP16 accumulations. If you need more, FP4 IN4, microscaling per tile with per-token normalization makes 4-bit practical for attention mats. For KV cache, PQ-based compression works. Train a tiny dequant helper MLP to reduce distortion. In all cases, normalize heads separately, per head scales, smooth outliers in QK channels, and never drop softmax normalization precision below FP16 unless you've validated long context stability.
Also, when quantizing gates or deltas in linear models, dequantize around the gate sigmoid, or tanh, to avoid saturation. It's cheap and prevents a lot of "why did my recall crater" moments.
Let's hit dynamic sparsity. How do you avoid making it a control flow nightmare for the compiler? Encode dynamic choices as Varlan segments. Mobe's trick is representing selected blocks via segment length tensors so kernels stay vectorized. Do not branch per token. Group queries by sparsity pattern and process as batches with shared masks. Also, share sparsity across heads like GQA. One pattern per group makes memory access regular. In short, simulate dynamic within fixed shape kernels.
Routing has the same pattern. Avoid per-token dynamic calls. Pre-compute top K indices per chunk, and pack tokens contiguously per expert. You can even keep K fixed and insert null experts to emulate adaptivity. The system breathes easier.
A knowledge platform team used this approach. Learned prefill masks, shared sparsity per head group, and KV paging on decode. They sustained 64K to 128K contexts on mid-tier GPUs, with recall in line with dense baselines and throughput up roughly 2 times.
Diffusion deep dive, sampler details, and where it fits in a portfolio.
Practical sampler, 5 to 8 steps. Cosine schedule over mask ratios with stepwise teacher forcing early in training. At inference, use confident decoding. Predict many tokens per step, but only commit the high confidence subset. Keep the rest masked for the next step. Blockwise AR keeps dock length flexible while preserving parallel denoise inside blocks. What's it good for? Forms, table-structured outputs, and fill-in-the-middle editing. And the bidirectional attention eliminates reversal quirks common in AR.
Systems-wise, fewer steps mean higher batch efficiency. FA3 FP8 kernels plus producer-consumer pipelining make it competitive. We've also seen good overlap with CPU-side KV caching when you only verify a small denoise subset each step.
For multi-turn agents, diffusion is less mature. Left-to-right state helps track tool calls, so keep it as a specialized decoder alongside AR for now. Hybrid portfolios are rational.
We promise surprises. Give me a contrarian implementation insight. Here's one. Many teams over-engineer attention while their allocator is the real villain. Pre-allocate KV slabs, pin expert buffers, and fuse tiny ops before touching the model. Memory churn steals more latency than you think.
Another, log linear memory, O log n read cost, is often enough. You don't need perfect O1 if your prefetch window is well engineered and your anchors are placed. Aim for asymptotics that match your observed n, not theoretical extremes.
And one more. MOE quality deficits are usually routing issues, not expert size. Balance loads, reduce gate temperature, add a shared expert. You'll regain quality without extra compute.
Let's talk testing. How do you know the change didn't just move the bump under the rug?
Use a 2-tier harness: microbench, kernel throughput, HBM traffic, SRAM hit rates, and macrobench, end-to-end latency at P95, P99 under realistic batchings. For quality, track long context recall suites and instruction win rates, freeze prompts and measure weekly. Adopt a no more than 1 point regression rule per KPI and require 2 green weeks before rollout.
Instrument cache hits, block mask sparsity realized versus predicted, and gate load histograms. If expert loads skew, specialization suffers. If block sparsity diverges from target, your distillation underfit. Retrain the learner.
For hybrids, run layer sensitivity analyses. Flip each dense layer to linear one at a time and measure perplexity delta. Protect the top 20% most sensitive layers. Those are your anchor positions.
Do we have a clean bill of materials for a modern, efficient LLM stack? BOM, FA2, FA3 kernels, grouped latent attention, GQA, GGLA with quantized QKT, training-free prefill sparsity, learned gate and KV pruning, heavy hitter page, chunked parallel linear layer kernels if hybridizing, pinned pre-allocated KV and expert buffers, ENT8 or FP8 paths validated for your head DIM, speculative decoding with shadow KV and CPU offload when context is very long.
Modeling BOM, gated linear memory with delta updates, dense anchors every 4 layers, sparse global cache for critical pairs, mild L2 on S, normalized feature maps. If MOE, small router, global batch balance, shared expert path. If diffusion, random ratio masking, confident decoding, and structure priors.
Operating BOM, profiling dashboards for I/O versus compute, cache heat maps, routing stats, canary deployments, rollback scripts, and an efficiency backlog prioritized like features, because speed is a feature.
Rapid case bullets, 3 sectors, 3 patterns.
Search relevance, prefill sparsity plus GTA KV paging, 2 throughput, near equal NDCG, customer support, GQA plus INT8 plus FA2, 35% latency drop with no fine-tune, regulated reporting, diffusion decoding with structure priors, fewer format errors, and faster batch generation at similar task quality.
Multilingual assistance, fine-grained MOE with global batch balancing, domain-specialized experts, and 1.7's token sec at ISO quality. Engineering docs, hybrid linidense with LoRa realignment, 2x prefill on 256K contexts, improved long-span cross-references.
Video text pipelines, axial dilated sparse attention and grouped KV across modalities, memory footprint shrinks, enabling 4 times longer clips per node. Quick debate, test time training, practical now or not yet? Not yet for mainstream serving. Blockwise gradient descent underutilizes GPUs, often 5% occupancy. You'll blow your SLOs.
True for microsteps, but with large chunk updates and dot product losses, you can amortize. Pair with local softmax and run updates only at chunk boundaries. Still niche, but promising on certain long analytical tasks.
Treat TTT as a targeted tool. Offline analytics or batch jobs first. Don't put it on your hot path unless the win is proven.
Before we close, one-liners of Do This Monday. Flip to GQA, enable FA2A3, and quantize QKT8, measure P95.
Insert dense anchors every 4th layer, linearize the rest with gated recurrence, and LoRa align on your top datasets.
Upcycle one service to MOE with global batch balancing and a shared expert. Start low K and watch loads and win rates.
Pilot blockwise diffusion for structured outputs, forms, tables, code fill, inferred in 5-6 steps with confident decoding.
Stand up an efficiency dashboard and make speed a first-class roadmap item. What gets measured gets managed.
That's part 2. implementation truths from kernels to routing, from hybrid memory to diffusion sampling. If part 1 argued that speed always wins, part 2 shows how to build it without losing your edge. Thanks all for the candor, the contrarian takes, and the field-proven recipes. Before we sign off, let's land the plane with an end-to-end synthesis, kernels to caches to models to business impact, so listeners walk out with a blueprint and not just a bag of parts. At the systems floor, the golden path is simple. Make the fast path fast. Flash attention 2 for today, flash attention 3 on Hopper with TMA WGMMA tomorrow, row-wise tiling, online softmax, and interleaved matmul softmax keep SRAM hot and HBM quiet. Decode is bandwidth bound, so shrink KV with GQA, GA, GLA, quantize QKT to int8 or FP8 with per-tile scales, and pre-allocate KV slabs to stop allocator churn. Amdahl's law absolutely applies. If 70% of your time is KV loads, optimize that before touching the model.
Modeling-wise, think associative memory with governance. Linear attention, linear RNNs, and SSMs are the same animal. A state S that writes with gates, alpha bay, and reads with queries. Add supervised forgetting via delta rules so S can unlearn mistakes fast. Keep dense anchors every 4 layers to preserve precision phenomena that softmax nails. For long context, a hybrid memory stack, local softmax for recency, gated linear for mid-history, sparse cache for critical pairs. Beats any one trick. Normalize feature maps and cap if you see drift.
In MoE, quality problems are routing problems. Use tiny routers, drop the aux loss if it fights the LM objective, and balance globally across microbatches so experts specialize without starving. Null experts emulate adaptive K with fixed control flow, and a shared expert gives you a safety rail. Operationally, pack tokens per expert in contiguous buffers and align all to uniform shapes. Efficiency is largely about traffic shaping.
Diffusion LLMs earn a spot when you need structured outputs and parallel decoding, random ratio masking and training, 5/8-step samplers with confident decoding, and blockwise AR to keep length flexible. Bidirectional attention eliminates reversal quirks and makes fill-in-the-middle native. For reasoning, SFT on traces plus a 1-step RL estimator closes much of the gap with AR. Today it's a specialist decoder, not the only one.
Strategy translation. Sequence your bets. 1. Turn on FA2, FA3 and grouped attention for immediate latency wins. 2. Prune prefill with learned masks, then page KV on decode. 3. Hybridize or linearize selectively with anchors and LoRa realignment. Scale capacity with MoE plus global batch balancing. 5. Add diffusion decoding where format fidelity and parallelism matter. Govern the rollout with a tight KPI quartet. P95 latency, token sec per GPU, long context recall, and top 5 task win rate, and insist on 2 green weeks before broad release.
Quick highlight reel. What's the one innovation that moved the needle most in your lane? Producer-consumer pipelining with FA3. Once you overlap TMA prefetch with WGMA compute, you unlock the GPU's real personality.
Delta rule fast waits in gated linear memory. Finally, a principled way to add and erase associations on the fly without retraining.
Global batch load balancing. Expert specialization took off the moment we stopped enforcing balance at the microbatch.
Confident decoding. Parallel denoise but only commit what's certain. It's the practical bridge between diffusion elegance and production reliability.
Grouped latent attention as a day 1 lever, it cut KV cost without upheaval and, well, made everything else easier to justify.
Let's do one last mini debate. Full linearization versus anchors and hybrids. Where should teams lean first?
Hybrids keep softmax anchors. Over-linearizing can sand down rare event precision and long-tail recall, measure layer sensitivity, and protect the top quintile.
Agree on anchors, but don't linearize before you've harvested grouped attention, IN8, QKT, and KV paging. Those alone carry you to 256K context on mainstream GPUs.
Sounds like consensus on sequencing. Cheap reversible wins first, deeper rewrites when the curve flattens.
Business takeaways. 3 crisp patterns we saw repeat across sectors.
Search and knowledge, prefill sparsity plus GTA paging doubled throughput with steady relevance. Customer support, GQA plus INT8 plus FA2 trimmed 35% latency and stabilized spikes. Regulated reporting, diffusion decoding reduced format errors and sped batch jobs with equivalent task quality.
Multilingual assistance, fine-grained MoE with a shared expert improved domain coverage and tokens sec at ISO quality. Engineering documentation, hybrid linears dense with LoRa recovered cross-ref accuracy while having prefill on 256K sequences.
Video text stacks, static sparse patterns, axial dilated, and grouped KV made 4 times longer clips feasible per node without swapping. Same I/O playbook, different modality. Pitfalls to avoid. Say the quiet parts out loud. Dynamic sparsity that branches per token, encode as Varlan segments and batch shared masks, or your kernels will thrash.
Feature maps with unbounded variance, normalize, or you'll chase exploding activations. And yes, log linear memory is often good enough for human timescale tasks.
Overhot routers, lower temperature, add a shared expert, and watch load histograms. Don't scale experts until routing is healthy.
Overstepping in diffusion, past 8 steps, returns fade. Spend the budget on better masking schedules and structure priors instead.
Final heuristics, sticky ones folks can tape to their monitors. Bytes moved, beat flops wasted. Optimize memory traffic first.
State is a promise, not a stash. Govern your memory with gates and norms.
Balance begets specialization. Healthy routing makes big sparse models feel smart.
Parallel when you can, auto-regress when you must. Pick decoders by constraint, not fashion.
Speed is a feature. Treat efficiency work like product work with roadmaps and release notes.
End-to-end wrap. We started with kernels that respect I/O. We shrank KV with grouped and latent tricks. We layered on hybrid memories with delta rule learning. We scaled capacity with balanced MoE, and we opened a new door with diffusion for structured parallel generation. The through line is co-design, algorithm, system, and business case marching together. Or, to borrow a classic line, slow is smooth, smooth is fast. If you stage the transitions, speed compounds without sacrificing quality. Thanks to all of you for the candor and the craft, and to our listeners. Your next 10% latency win is probably hiding in your KV cache, your allocator, or your router. See you in part 3, where we turn these blueprints into a live migration diary.